All right, we're all here that are going to be here. Well, except for Clayton, stepped out. We are going to continue talking about the sun. Hopefully, lab last night was fun. I know it was a little brief. You should have a better feel for what you're going to need to know and how much you do know. So if you were struggling, you know what you need to shore up on. Let's talk more about the sun. I think I ended with this slide. I may have stopped one before this slide. The sun, on the surface of the sun, you have some really cool things that happen. You have prominences where you have the plasma shooting up and coming back down. And what did I say these were following? I did do this because I remember talking about that.
Magnetic field.
They're following magnetic fields. Now, I didn't include the figures from the lab book or from the textbook about how we know they're magnetic fields, but it's called the Zeeman effect. The emission lines, remember we talked about the emission absorption lines. The emission lines actually will split if you're in the presence of a magnetic field. And the amount that they split, that is the wavelength splits from the original, tells you how strong the magnetic field is. So we can actually measure the strength of magnetic fields on the surface of the sun by looking at those. And when they look at sunspots, you see it in absorption line, actually in this case. You see an absorption line that's just a straight line as you scan across the sun. And then when you get to the sunspot, all of a sudden it splits off. And then after the sunspot comes together. So that tells you you went from a reasonably small magnetic field, comparatively, to a strong magnetic field you can actually measure by the split and then back when you went across that sunspot. And so where these things are coming out and going in are where the sunspots are. So there's one here and one here. So that's why they come in pairs. Then we have really cool things, solar flares. These are magnetic field things. Right? The magnetic fields are what's guiding this. Well, sometimes those magnetic fields get all kinds of wacky and they snap, so to speak. Think of it kind of like you stretch a rubber band too far and it snaps. Now, magnetic fields are kind of unique things, but what will happen is it will essentially burst and a huge amount of energy goes flying away when that thing bursts. And so that's what we call a solar flare. When solar flares happen, that really affects us if it hits the Earth. In 1857, there was, well, there's two things. I should talk about the other thing. Often associated with the solar flare is a coronal mass ejection. The corona is the crown, right? That's what it means. And it is the material that's very hot that's surrounding the sun. Well, oftentimes when you have a solar flare, when you have one of those things snap, you'll have a huge eruption from that corona that blows huge amounts of material away. So we have two things actually that send stuff flying toward us, the flares and the coronal mass ejections. And I don't care which one causes it. When all of the charged particles come and hit the Earth's atmosphere, well, the Earth's magnetosphere, the Earth's magnetosphere responds. It basically flexes because of all these charged particles coming at it that it's trying to deflect. And so the change in the Earth's magnetic field will then cause large magnetic field changes here on the surface of the Earth. And you might think, so what? Worst case scenario, compass wavers, right? Not the worst case scenario. In the early 2000s, there was a power generating plant up in Canada that was knocked offline because when you have a sudden change in magnetic field, it produces currents in wires. It makes electricity flow. And it caused the electricity to flow in the power plant, knocking it out. In 1857, there was a massive event that devastated, well, if it happened today, it would devastate us. In 1857, they were just developing telegraphs. And they had the telegraph wires had enormous current surges because of another event like this. And it basically knocked out all of their electronics they had at that time, which was all very basic things. If it were to happen today, every electronic thing you can imagine would be dead. Our cars, they use things like electronic ignition these days. Your car wouldn't work. Everything would be knocked out pretty much that uses electricity. So that is something that could be very devastating to us. And what can we do to protect ourselves? Virtually nothing. Best case scenario, it takes about 8 minutes for light to go from the sun to us. And so we'll know it's coming 8 minutes after it happens, and it will take at least hours for it to get here. So, you can have a global warning, it's coming, it's coming. Put your electronics in a Faraday cage. You can put them in a Faraday cage, then you can protect them. But, you can't do that with everything, and it would be devastating. So, this stuff is something we hardly talk about, but it's something that could be devastating. Now, I want to show this video, and of course, you saw all the problems I had last time, so I'm going to load it up on the other computer and switch over. And I'm going to show a video of what's going on in the atmosphere of the sun when you have one of these coronal mass ejections, because they're very cool. And, if there's something very cool, I've got to show it. It's one of those rules you learn. The hard part is typing in this URL. Hoping that YouTube's back up. You guys probably saw that YouTube was down yesterday.
I heard about it, but it never had an effect on all of you. Yeah, it went down a bit, and I was going to go. What done? Okay, so this is going to be affected YouTubers, so.
It's no longer available. Okay, well then. This is not the same video. Actually, it might be the same video. Who knows? Is that awesome or what? Really? I was thinking there should be sound with it. Well, then what we do is we turn this off. And we turn back to the beginning of the video. There you go. I was wondering why I didn't have sound, but didn't notice anything else. Very useful sound. This is what I really want to see. The thing, notice it has a block for the sun because you can't take pictures without your telescope. And you see all the stuff that's always blowing away, and then you just see the huge burst. Totally cool, right? You tend to not realize the sun is doing crazy, wacky things like that. Oh no. That was the video. I was like, where's that coming from? Okay, back to, there we go. Okay, back to the presentation. So those coronal mass ejections are major things. Something you've noticed me saying over and over is the sun is blowing stuff away. And so sometimes you think, well, if if I were to blow stuff away like money, if I were to throw away $10 every day, pretty soon I'd be broke. The sun is blowing away lots and lots of material, but it's so massive. You know, it could blow away an Earth's worth of mass every day, and it would take a million years for it to really matter. So it's not losing any significant portion of its mass. It is losing mass, though, constantly. Okay, now obviously we're not using clickers this year, but a question just to make sure that we're up to speed here. What is the surface of the sun that we see called? All right, we've talked about the surface of the sun. What is it? What's the name of that? The photosphere, because that's where the light comes from. Now here's a picture showing the different regions of the sun. So here we see the photosphere, which is where you have the sunspots. Here we see the chromosphere. What causes the chromosphere? It's called chromo because of color, because of the emission lines from hydrogen. So we have that chromosphere, and you see it's a different color. It's a pinkish color. And then we have the corona out here, where you have all of the very hot material that crown around. A coronal hole is a hole in the corona. What would cause a coronal hole? Well, if you have a coronal mass ejection, it will leave a hole. And by the way, the energy of those is so large that oftentimes you will rebound and you'll have one on the opposite side of the sun as well because of the rebound. This other picture is showing how temperatures vary. Temperature on the surface of the sun somewhere between 4,200 kelvins up to around 6,800 kelvins. It's the temperature in the region of the photosphere. You go up to the chromosphere and it will go up to around, 50,000 kelvins. And then you go up to the corona and it gets into the millions of kelvins. So that temperature profile is kind of interesting to look at. Now, sunspots. Probably the bulk of today's lecture will be on sunspots. Spots are surprisingly really important to us. Sunspots, here's a picture of sunspot. You can see that there is a pair that's very prominent. They usually come in pairs, and if you look really carefully, you see there's a pair there, there's a pair here. Some of them, it's hard to see the pairings. This one, I think, is a pair separated by that, but it's hard to see it. But they come in pairs. And those pairs, well, first of all, let's make sure we're clear. Why is it darker in here than it is out here? Cooler. The temperature might be around 4,000, well, let's go with 4,200. 200 kelvins versus 5,800 kelvins. And any reasonable person says those are both big numbers. But in terms of the amount of light they give off, the luminosity is proportional to temperature to the fourth power. So if I do the luminosity of the sunspot divided by, okay, and when I say luminosity, now I have to do the luminosity per unit area. The equation for luminosity is there. Now my work will be exact. The luminosity per is that. So luminosity for a sunspot divided by luminosity for the rest. And so if I put in the numbers that I have, just changing pen color so I can write on the yellow. That's a 4. You put that in the calculator, and it comes out to be a surprising number. and it's 27%. 0.275 if you want to go. So you have only 27.5% as much light coming from here as you have from here. And that's why this looks dark, because it's about 1/4 as much light coming from it. It's still hot compared to anything on Earth. It's still giving off lots of light. Well, I say compared to anything you're used to dealing with. Still giving off lots of light, just not nearly as much as the rest of the sun. These things move. We can observe them on the surface of the sun. And so here is a sequence of pictures going from March 25 to April 2, and you see them going across the sun. What would that indicate? Just think about the scientific method once again. You find something interesting. The positions are moving. They're moving as a group, although you do see some change. Clearly, the left picture, it looks very different on March 26th than it did on March 27th, right? It developed more by March 28th. But you see something interesting. What's the next step in the scientific method? Well, you create a hypothesis that explains why it happens. That makes a prediction. It needs to be based on scientific ideas. And so this one here doesn't take a genius to come up with the right hypothesis. The sun must be, what must it be doing if it's moving across the surface of the sun? Must be rotating. And so then you look and you try to examine it more carefully, and you know what scientists have found? It's a different rotational rate depending on where you are in the sun. We call this a differential rotation. When you have a fluid, something that can flow, that's not rigid, you can have different parts rotating at different speeds. And so, looking at the sun, at the equator, it takes about 25 days, notice there it's 25.05 days, for it to go all the way around. If you go up to 40 degrees, and I wrote these on my hand so I wouldn't forget, it takes 28 days to do a cycle. And if you go up to 80 degrees, essentially at the pole, it takes 36 days according to our textbook, 34.3 days according to that textbook. Did check to see which one was right. And so we have a quicker rotation at the poles and a slower rotation, or excuse me, the other way around. 34 is a bigger number, which means it's slower rotation. So a quicker rotation at the equator, a slower rotation at the poles. The sun is not the only rotating fluid object we have in our solar system. We also have all of the Jovian planets. And the Jovian planets also show this differential rotation. So here I have, on Saturn, the pole takes 26 minutes less time than the equator. So on Saturn, the pole is rotating faster than the equator, just the opposite of the sun. On Jupiter, the pole is 5 minutes shorter. That means it's, once again, the pole is going faster on Jupiter than the equator is. So the sun is opposite of those two, going faster at the equator and slower at the poles. Interesting, isn't it? Now, the time for Saturn and Jupiter, 26 minutes and 5 minutes out of roughly 10 days, is a much smaller percentage differential rotation than on the sun, right? The difference there of 9 days out of, let's say, 25 is a much bigger percentage. Well, this has a significant effect on the sun as we understand it. Because when you have different speeds of rotation, you have magnetic field lines that are going like this. If the magnetic field lines are going like that and you have charged particles rotating at different speeds, you're going to drag the magnetic field line at different speeds for different parts of the sun. So the magnetic field lines start to get tangled up. And that explains what's coming up on our next slides here. So our textbook says that the observations started in 1834 to 1855. Somebody was studying very carefully the sunspots in the sun because he was trying to find a planet closer to Mercury and was hoping he would see its silhouette as it passed in front of the sun. Never saw that, mostly because no such planet exists, but he saw a pattern in the sunspots. Now, I said the textbook names that in 1830s to 1850s, but we have sunspot data going back to 1755. So that's not the first observation of sunspots. It's just this first really detailed. We have had 24 cycles of sunspots. What that gentleman noticed very keenly was that we have cycles of solar activity. And so there's two things that are being plotted here. Now, these are both showing from around 1870 to 2015. You have the amount of sunspots per, it says average daily. And you see not many more, not many more, not many more. And you see that, wow, here 1950, 60, 70, 80, 90, those were all very heavy periods of sunspot activity. The sun was behaving differently then than it was in the early part. If you look at the locations of the sunspots, you see that when the sunspot is starting, when you're starting to get more sunspots, they start occurring out here at latitudes that are in the ballpark of 30 degrees north or south of the equator. And then as this peaks and dies out, they move closer to the equator. So it's very curious. If you're going to have a hypothesis to explain these sunspots, it needs to explain why you have the cyclical nature, and why the sunspots start farther from the equator and then come in toward the equator. So, let me back up one. There was one important thing that I didn't say there. Every 11 years or so, you have a repeat in the cycle. It actually varies between 9 to about 14 years for the cycle. Some are longer, some are shorter, but it's pretty reproducible. The Earth, I'll just come back to that later. So around 5.5 years after the solar maximum, sunspot numbers, that's the lowest. Why? Because that's halfway between. This is the answer that scientists have given for why we have this cycle. And it's based on more details than just what I've given you. For instance, they come in pairs, the sunspots. One has a north magnetic field, one has a south magnetic field. And every time it switches, or every time you start a new cycle, the one that's leading switches. So you'll have north leading, and then the cycle stops and a new one starts, and you'll have south leading. In fact, as I was preparing for today's lecture, I was reading up on the current activity of the sun. We are at the very end of solar cycle 24. The 24th cycle since 1755 when this was first observed. And some people have said it looks like we're already starting to get sunspots from solar cycle 25 because of the reverse in polarity of which one's leading. Right? That's a way you can tell which cycle it's from. So here's the theory. We have magnetic field lines with the differential rotation, so they start to bend. And as time goes on, they bend more. And so they start getting tangled up. And as they get tangled up, they start shooting out in funky directions. And when those magnetic field lines come out through the surface, then we have our storms on the sun, our sunspots. Why is it cooler? I told you once, and I didn't give you any good reasons. Because of the strong magnetic field coming up through the surface, that strong magnetic field suppresses, it stops the convection action. Remember, we have those granules of hot material floating up. The strong magnetic field suppresses that. And so you don't have hot material floating up, hence the surface is colder there. We don't have hot material floating up. And so that's why it's dark there. Now, why would any of this be important? Give me some reasons. We already have some, and there are other ones that are even bigger. But what already do we have that would be important about these sunspots? Think all the way back to the beginning of the lecture.
Doesn't it help us see a little bit about the rotation of the...
Okay, it does help us to observe the rotation. What I was really shooting for was, when the sun has more activity, it's going to have more flares and coronal mass ejections, which is going to have more impacts on us. if we have a solar flare that comes and hits the Earth that isn't devastating, then we all go, woo, because that's when you see the northern and southern lights. Because the charged particles coming into the atmosphere excite the atmospheric gases to higher energy levels, and electrons drop back down and give off the light, the northern lights. Okay, another reason this is really important is it turns out that there is a strong correlation between global temperatures and what's going on with the sun. Now that makes a lot of sense. Our textbook says that the difference in solar radiation, that is how much total energy is coming to us from the sun, only differs by about 0.1% between when we have heavy action and light action on the sun. And that it says that that couldn't explain temperature fluctuations on Earth with such a small change. I actually don't agree with that. I've read other places that did it, said, that because the Earth's energy budget is 99 point something percent from the sun, just a small change in energy from the sun is going to make a difference on Earth. But I'm not an expert in the field, so I can't actually go and deny it. But here are some graphs that show different things about the sun. First, the bottom graph. The bottom graph is a really important one. This is showing sunspot numbers. Notice we don't know anything about the cycles here, but the number of sunspots were first observed by, I believe, Galileo, right? Looking at the sun with his telescope. And the numbers out here are not going to be super accurate, but we went through a period from about 1650 to about 1720 where there were virtually no sunspots. Virtually no sunspots has a result that the sun gives off less radiation. Now, there's a lot of interesting things that go on. For instance, when you have a sunspot, of course you're getting less radiation from the sunspot because it's colder. But the area around is giving off even more because that energy has to go somewhere. So you have more sunspots, you are giving off radiation. So this time period when there was very little solar activity, you might be able to predict what happened on Earth during that time period. It got cold. We call it a little ice age there. The Earth got colder. In London, the River Thames would freeze over in the winter, and they would have ice skating parties on the River Thames. But then the sun returned to normal activity. And when the sun returned to normal activity, temperatures started rising again. You see there's another drop there around 1800. There are a couple places that are called minima. The Maunder minimum, though, is the obvious one that nobody can deny. There's something serious going on there. So if you look at global temperatures with respect to the sunspots, what you see in general is the global temperature follows that. For instance, what's been going on for the last 100 years or so, temperatures have been slowly rising, right? And if you look at the solar activity has been slowly rising over that period. Except there's a little drop here. And you know what? That's just about the time that scientists started getting worried about global cooling. That man was causing pollution, and that pollution was blocking the sunlight and causing the Earth to get cooler. And that we would have to stop our pollution or the Earth would go into another ice age. But then the Earth got warmer again and continued to warm. And now everybody says the Earth is getting hotter. We have global warming caused by pollution. And we're going to have to stop polluting or we'll burn. The ice will melt, the sea levels will rise. I still say Al Gore doesn't really believe this, or else he wouldn't have all of his carbon-consuming stuff. Right? Just because you go plant a forest doesn't mean that you are immune to pollution. Anyway, it is clear that the sun has a definite effect on the Earth's temperature. When the sun is more active, the Earth is hotter. But this top right graph, oh, by the way, this graph here is just more detailed information from what you get here looking at the average line. But this graph here tells you that maybe Al Gore isn't all wet. Because what you see here is the number of sunspots in red, and what's happened to the sunspots in the last 20 years. Go ahead, you can say it. It's decreased. According to this graph, what's happened to temperatures? They've increased. That's going opposite directions. Now, you may have read things about climate scientists trying to make the data look like there's warming when it's been staying kind of constant. I don't know exactly what to believe about that. My overall feeling has always been that the Milankovitch hypothesis is a very strong hypothesis. Milankovitch, who was he lived in the late 1800s, early 1900s time, he said that I think that the Earth's climate, the global climate, is predicated by nature. And so he listed, I think, 7 different things that climate will be affected by. Those include the solar activity, which we have really no predictive power on. We can say we think what's going to happen within the next 30 years, which I'll talk about in a minute, but we can't say what's going to happen in 50 years or make a prediction there. But then we also have things like the eccentricity of our orbit. Remember, eccentricity is how elliptical it is. Our eccentricity changes over time because of the effects of the other planets. And so when it's more eccentric, we're going to have bigger seasonal variation. When it's less eccentric, we'll have a smaller seasonal variation. It depends on which hemisphere. But then you have the tilt of the Earth. Once again, the tilt of the Earth actually changes between about 24 and 22 degrees over time. And so that's going to make a difference. The time of year when the Earth is closest to the sun makes a difference. All of these different things come in together, and Milankovitch then you can, with his hypothesis, predict what global temperature should do based on all these factors. And the predictions of the Milankovitch hypothesis have matched very closely the Earth's temperatures over a significant period of time. But if they're diverging now, then I would say, aha, there's another factor, likely man. Well, here's the key detail that I like for all of this. Here's what's going on right now. Solar cycle 23 lasted extra long. And scientists said, if it's lasting extra long, that, we believe, according to our models, means the sun is cooling off on the activity. That we're not going to have as many sunspots, not as much radiation from the sun. And sure enough, you can see that solar cycle 24 was nowhere near as big as solar cycle 23. The maximum, I read the prediction from 2008 that said they thought it reached minimum right about here. Turns out it didn't reach minimum until about here. Sue them. They said they predicted it was going to reach maximum. I think it was around here, and it actually didn't reach maximum until here. They were 11 months off in their prediction for maximum. They were pretty accurate, really. And if we go back one, you can, actually, this doesn't show. Yeah, it is. This is number 23 here. And so you see number 23 wasn't as high as 24, which wasn't as high as, 22, which wasn't as high as 21. Now 20 here was a small one, but then 19 was the biggest one we've ever recorded. So we've had some fluctuation, but now they believe that it's really going to be tailing off. And if it's really tailing off, then that means that we should really expect global temperatures to drop if nature is what's driving our climate. If it's man-causing effects, well, then we won't. So, I would say by 20 years from now, by the time you guys are in your early 40s, there will no longer be debate if man is responsible for global warming. It will be either we cooled off, it wasn't man, it was the sun, or we didn't cool off, we screwed up big time. Now, anytime I talk about this, I'm kind of skeptical about the claims that man is responsible for global warming. But I also believe that as a Christian, I have a responsibility to this earth to maintain and protect it. And that means to not be a polluter. So whether man is causing climate change, I still think that we need to protect the environment. And so it really annoys me, that President Trump, for instance, has taken away many of the things to protect the environment. Even if I'm skeptical that man is causing global warming, I still want to protect the environment. Okay, now switching to what's inside the sun. We've talked about the surface of the sun and a little bit. We're going to shift to looking inside. And inside the sun, of course, I said we have a nuclear furnace where hydrogen is built into helium at a temperature of millions of degrees. We want to learn more about that. So the first thing is this hydrostatic balance. The solar thermostat, the thing that sets how quickly the sun is going to fuse hydrogen to helium, is the balance between the energy release in fusion and the gravitational pull. So at every place in the sun, as you get closer to the center, you're going to have more weight to the stuff above, so the pressure goes up. And you're going to have a balance going out from the center, or else it'll collapse. And so everywhere in the sun, we have that balance, so it's called hydrostatic equilibrium. So the pressure in the center is going to be really big compared to outside. Now, what difference does that make for fusion? Fusion is when two protons, it's actually a proton and a proton come together, and they go off and they make a deuterium plus something else. And then you have two of these meet, and it creates, it's a combination. Two of these meeting will create a helium-4. Actually, it's not that simple. That's the net reaction, but it's not the true reaction. So you're having these things coming and hitting each other. Well, protons, hydrogen nuclei, have a positive charge, and opposites repel. So you can't just take two protons and bring them together. You have to force them together with a lot of energy. Now, I say you have to. How is this done in the sun? You simply have to have protons going fast enough that their energies will bring them together. If they get really, really close, there are a couple forces that normally don't act that will hold them together. You have to get them really close. You have to have really high energies, which translates into high speeds, because there's kinetic energy. And high speeds means high temperatures. So the temperature has to be really hot to make fusion occur. There's also a pressure thing. If you have low pressure, the chances of two nuclei hitting each other head on is pretty slim. But as pressure goes up, the likelihood gets bigger. So in order for fusion to occur in the sun, you have to have both a high pressure and a high temperature, which is what is created by the gravitational pull. And of course, when you have the explosion, when they actually fuse together, it's going to a much lower energy state. And it gives off a lot of energy because it fell to a lower energy state. Just like I dropped this, gives off the sound energy. Not very much because this stuff wasn't very hard. It was a bad example. Here, let's take this. Yeah, if I drop this, it makes a lot of noise, right? But the energy is coming out, and so that's the outgoing energy that's balancing in falling energy. Everything here is based on observations from the surface and modeling. None of this is based on us passing a thermometer through the sun or anything like that. But we believe that the sun, of course, out here you have the corona in the farthest out. Then you come into the chromosphere, you see the pretty colors. Then the photosphere, and then you go in, and you have first the convection zone, the place where you have mixing because hot things expand, and because they've expanded, they're lower density, and lower density things float up on higher density materials. Just like styrofoam floats in water, because styrofoam is less dense than water. So that's what's going on. I'm going to zoom in. Whoops, maybe I'll zoom in. I'm only going to try once more, taking the stats out of my hand. Nope, not going to try to zoom in then. So we have convection out here. Inside we have what we call the radiative zone. And the first question anyone should ask is, how do we know there's a radiative zone inside? How do we know it's not convection from the core out? There are two lines of evidence to answer that. One is called helioseismology. Let me go forward to the next slide. Oops, not that slide, not that slide, that slide. The sun has sunquakes. The sun will have waves that go through it. When you have a coronal mass ejection, remember I said the rebound will often cause something on the other side as well. So scientists study the motion, the jiggling of the sun. And just like with Earth, we can use seismology to determine what's going on inside the Earth. We do the same thing with the sun to determine what's going on inside the sun. So they have ways of determining actually what the density is like in the sun based on the speeds of waves going through the sun. So it's not completely in the dark, haha, very funny, to come up with these. Second thing is how we understand the processes that can occur. And things like, I talked about the granules, you have the supergranules that are convection from lower. Well, they calculate based on the size of the granules how low it could be coming from. So they have a couple different things to tell you. There is a break between where you have convection and where you have no convection. Now, if you have no convection, the only way heat can transfer is through radiation. Light is radiation. Now, in this case, we're talking things that are really hot. So according to Wien's law, the wavelengths are going to be much shorter on average for the radiation. So you have this very short wavelength radiation that's carrying energy out from the core. Problem. You also have lots and lots of atoms in there. And every time the radiation gets to a new atom, it gets absorbed, re-emitted. And so you have what in physics we call a random walk problem. The random walk problem is always stated this way. You have a drunk person that steps out of the bar. And he's so drunk that every step goes in a random direction. So you're like, and then you calculate how long it's going to take you to get to his car. Yes, that's the kind of problem we have to do in this class. That calculation can take at least 100,000 years for energy from the core to reach the end of the radiative zone where you have a convective zone. The reason it takes so long is because of the random directions. It goes this way, that way, that way. The average motion, the average position is always the center of the sun, but the probability for the radius is getting bigger. And so that's where they come up. Some people have said a million years, for the average energy to get to the end of the radiative zone. But once it gets to the convective zone, the heat's flowing in one direction, out, because hot stuff flows out. So it's pretty quick once it gets to the convection zone. Now, meanwhile, temperatures. As you go further in, the temperature is rising. So here we have the temperature profile around 6,000 kelvins, right, 5,800 kelvins at the surface, the photosphere. Then as you come in, you see millions, 1.4 million, 3 million, 5 million, 9 million, 15 million kelvins at the core. That's our calculation. 15 million kelvins is really hot. If it was only a little bit hotter, like 16 million kelvins, the sun would be a more efficient machine. It's just below that efficiency level to go to a different fusion mechanism that's more efficient. You look at the density, remember we talked about the surface density. Well, the average density of the sun was 1.4 grams per centimeter cubed. But the core, it shoots all the way up to 160 grams per centimeter cubed. Super dense in there. And the core is actually a fairly small region of the sun. Notice it has a marking here for the core that's just 20% of the radius. And of course, if you take volume, volume is proportional to radius cubed. So 0.2 cubed is 0.0064, I think. No, 8. It'd be 3 zeros and an 8. 0.0008 or 0.08% of the sun's total volume is in the core. Very small region percentage-wise. I've already talked about the energy transportation. This is just a good question. How do we know that the sun has a radiative zone? Or radiation, yeah. How do we know? Well, let's do these one by one. Can we see it with a visible light telescope? No, we cannot. Can we see with a microwave telescope? No, we cannot. Can we see with an ultraviolet telescope? No, we cannot. We don't know. We predict it based on an understanding of physics. You know, with astronomy, I point this out probably every third lecture at least. What we think we know, we feel pretty solid about, but we don't actually know it. And that's the way it is in science. You're constantly moving toward more understanding. And so, you know, when we talk about things like we get to cosmology and the Big Bang, up until around 100 years ago, actually less than 100 years ago, it was assumed that the universe was just static. That the stars were just there doing their thing, and the planets were doing their thing, and everything pretty much stays the same. And then Edwin Hubble noted that things that were farther away were moving away faster, and they said, whoa, that means that everything must be expanding outward. And if you extrapolate backward, the reverse of expanding outward is coming together. So in the past, it must have all been together, and that's the beginning of the idea of the Big Bang Theory. And so scientists changed in a major way their understanding of how the universe worked. Were they wrong before? We assume yes. Are they right now? We hope yes. But it would be unwise to believe that they're absolutely right. But what we can say is they're developing and learning more so that we're getting closer to the truth. Which reminds me, October 27th, I believe it is Creation Sabbath. And so churches, SCA churches worldwide will be doing something special for creation. And they're planning something here. One of my colleagues is worried, what if people think that we're a bunch of liberals, you know, if we go up there and we talk about evidence for an older. Frankly, I think we should just talk about what the science says, what the Bible says, and how we interpret it, and not be judging on, you know, oh, do you believe that? Anyway, so I don't mind. Besides, you guys all know, what do I believe about the origins of life on Earth? Evolution. Okay, this is being recorded. Now, let's be honest. I believe in a divine creation. And I believe, furthermore, I believe that there was a Big Bang. But I believe that God created the laws of the universe and that God put the energy in for the Big Bang. There is no scientific answer for how the Big Bang could have started. The person who came up with the name Big Bang, it was in mockery. I think it's, Fred Hoyle? He was mocking the idea of what started it all. He refused to accept the Big Bang Theory because, as far as he could tell, it would require that there was a God. And he said, I'm an atheist, I cannot accept a theory that requires a God, so he rejected the Big Bang Theory. He later on accepted that there was a God, didn't become a Christian. He accepted that there must be a God because when he was studying the energy levels of nuclei, he said the chances of exactly the right energy level being what exists is virtually zero. It had to be designed by a God for it to exist. It's a pretty interesting story. Okay, I guess my time is up. Let's just end with this. What is the source of the sun's energy? And just to make sure we're clear, nuclear fission is when you have an atom that splits in half or into two pieces, not necessarily in half. Nuclear fusion is when you have two things come together to become one, kind of like a wedding. Combustion is burning stuff. That's a redox reaction. So you have, like a fire's combustion. Okay, the bottom two are laughably ridiculous. I put those in because I like to think I'm funny. Okay, so of those top three, let's forget the two funny ones. What is the source of the sun's energy? Is it? I thought you were putting up 4 fingers. I was like, no, that was.
It's solar.
Okay, so we have 1 vote for nuclear fusion. Any other votes? And yes, this is sign language for B. C, what is it? A and S, I get confused, right? A-S. Come on, guys. You use hand signs. Who do you like, Mira? B. Okay, so it's nuclear fusion. It's fusion of stuff. And so we'll study that next class period.